you need to have a signal collecting unit, right? How you connect the signal, and then you need to have a suitable pattern recognition software, right? This is how your brain, if you interpret as a human, this is how your brain recognize a signal, right? So basically, these are the concept of the enos. If we take a look, I think in 1982, I think I was born at that time, right? The first publication on the enos, right, was done by Prof. Krishna Prasad. And for your information, he's still with us again in the University of Manchester. I think Prof. Azhar met him a few months ago. Prof. Azhar invited him over the conference, I think. Right. So he's still healthy, he's still active in research, right? So he's the one that managed to publish the first journal in Nature. And I think if you heard about Nature, I think a lot of researchers wish to publish their work in Nature. It's not an easy task to publish the work in Nature. Right? Okay. The first enos that he published, he was mentioned that this device can keep on reproducing or discriminate wide variety of smell, right? And he showed that this discrimination can be achieved using a highly specific receptor. It was that time he thought that individual gas sensor need to be really specific, but later after they discover that they only need to be a partial, right? Meaning that it can not only detect a particular gas, but it can detect wide range of gases, right? To mark up the concept of our smell cells in our enos, right? Okay, so he was very successful. He was the first group dedicated to the smell, and then he managed to form many other companies, and he also involved a few other products that based on the enos, right? Similarly, Prof. Garner also managed to come up with the Saranos. I think if you Google around, you will see that Saranos. I think in my lecture, I'll show you some slide with the Saranos. These are the first device that they are working together. A researcher of 10 people, they are working together, come up with a very good enos. Until now, the Saranos still exists, right? And then the technology been passed over to other company, and the bigger company keep on buying the technology. Right? Okay. If you take a look on the market ataupun growth by the region, you can see that US, Europe, they are highly demand the technology of enos, right? So they are the advanced country that are aware of the enos technology, right? And then you take a look on the Africa, right? On the South America, right? They are less demanding, because I think the exposure is slightly low, right? And Malaysia or Asia, and you can see that we are quite exposed to the technology as well. I think our knowledge is quite okay on the enos, right? So I can tell that in next few years, I think enos will be part of our daily life. Okay, right. So if you take a look in Selangor, few months ago, right, there are a lot of water shortage. Right? I think this is because of some people throwing rubbish, throwing the chemical into the river. Right. The first thing that they're able to detect is from the smell released by the headspace of the river. Right. So this shows that the enos is a very powerful tool. Right. We should deploy everywhere. Right. Okay. I'll go through the application, current application of the enos, right? I think previously the enos start for the medicine or for the fragrance, right? Lately it merged toward the environmental and toward the foods, and now we are going toward the entertainment as well, right? I'm not sure what are the status for the entertainment. I think 2019, 2018, right? There are one conference in Japan. They are producing a digital smell, right? Meaning that you don't have to go to the shop to smell the perfume. You can sit in front of your PC, just click a few buttons, you can smell the perfume, right? This is what they are trying to do, right? I think there are more, things that they don't release yet so far, right? Okay, the first Enos was discovered when, I think you heard the story, if I'm not mistaken. The owner of the dog found that one day the dog keep on barking or behave differently. Later, he was discovered that he has a terminal cancer. Right, right. The dog can smell something different, emit from his breath. Right. That's why the dog keep behave differently, as if try to warn his owner. Right. From there, right, the scientists try to push the Enos application for biomedical, right? And then later on, they move into environmental. They move to food and beverages, fragrance, and so on. Okay, and then if we take a look, and in the previous slide, the Enos is quite big. Now we all are moving toward a smaller size. The sensors are getting smaller and getting sensitive, and what do you call it, from the bigger size, they are able to move to nanowire and so on. This is all thanks to the nanotechnology, right? So let's take a look the growth. I'm not in the background of economy. There are a lot of numbers that I also don't really understand, but you can see that the growth of the market at 11%, and the value of Enos is at 16 million, right? And then at the 2019, the growth was at 8.59. I think this is quite high, right? And then if you Google around, if you search in a Scopus, I think you will find that more than 10,000 reports or journal covering the Enos, right? Okay, let's compare the Enos with the actual human nose, right, or human brain. Right? For example, we have a source of gases, of source of smell, right? If Enos, we need a sensor. For example, we need an array of sensor, right? So once we have an array of sensor, we need to have electronic system to be able to retrieve the signal from the sensor, right? Once we have the signal, we will have an array of data, right? Once we have an array of data, we need to recognize, we need to train the system to be able to differentiate between different smell, right? So these are the challenge, right? There are three different challenge. One is how to receive the smell or gases, how to ensure that the gas sensor receive the smell, right? And then you need to make sure that the noise are being filtered before you put it in nice big table before you be able to recognize, right? If we take a look on the system, right, I think we have more than 10,000 sensor cells in the Enos, right? Each of the sensor cells are quite jelly, right? Some of them are tuned to a certain particular smell. Some of them are wide range. They can smell a lot of smell, but they are less sensitive, right? Uh, and then the signal are pushed straight away to the brain, and the brain can be able to differentiate slightly different smell, right? For example, let's say, right, you go into a bakery shop, right? You smell a nice bakery baked in the oven, right? At the same time, the smell is so strong, right? You couldn't smell, any other bakery around there. You could not even smell the strawberry jam. You could not even smell the other pie or so on, right? Because the smell are so strong, they overwhelm, and your brain cannot differentiate other smell, right? Only after you left the bakery house, and your sense of smell will become become sensitive again, right? This is also happening to the system, right? if the sensor exposed to the high concentration of gases, right? We need to be able to apply purging, right? The same concept. The nose is derived exactly the way how we human smell, right? If you take a look, right, when you're sniffing, right, at the same time you will hold your breath, right? And has anybody able to smell and take a deep breath at the same time? And please let me know, right? Right. Similarly, if you take a look on the animal, right, like say dog, for example, they used to search and rescue. You can see that the dog will keep on sniffing few times, and then it will release and then try to breathe, and then you try to smell two or three puff again, right? The smelling shouldn't be done in a continuous way, right? Meaning that you shouldn't smell. I mean, if you take a deep breath, you shouldn't continually smell at the same time. You should smell and try to, when you sniff, then you try to pause momentarily. Then when your brain say that, oh, I recognize this smell, then you exhale, right? Okay, this is how we as a human smell, right? I'm not sure. Maybe it is for me. When I smell a nice coffee, I will take a deep breath and then I hold my breath momentarily to make sure that I can really smell the coffee. Right? And then after that, I will push right from my nose, and then I will take another short sniff and push again. Right? We cannot continually sniff, and meaning that if we design a system, we cannot continuously draw from a palm. Right? You will not get a good result. Okay. For this, I think I'll show you a detailed concept of the enos, right? Okay. The basic enos, you need to have a baseline result, meaning that at normal condition, what sort of response that you'll get. Okay. Right. This is really critical, right? And then you need to have a headspace delivery system. This is what I mentioned earlier. Let's say if you want to uh, deliver some smell to the enos, you need to think something of the system, right? How are you going to sniff, or you want to let the machine to sniff the smell in the ambient, right? So you need to have a pump, right? You need to have a pressure sensor as a feedback, and then you need to mix, or you need to make sure that the sample goes to the sensor chamber, right? So this is your sensor chamber, right? Different color means there are different type of sensor, right? Once you're able to sniff, right, then you need to have another system to push the sensor chamber, meaning that you cannot sniff continuously, right? Maybe you sniff for a few seconds, then you sniff the filtered air and push back the chamber. Right? This is quite right. So that's why you need a very complicated system, right? And of course, you need a I think at the very beginning, when Professor Persout come up with his enos, he come up with the three gas sensor, and he was very excited that he managed to differentiate different smell, right? And of course, you need to have either to have a what do you call it, zero gas, which is fully air, or you need to filter the air surrounding of you, right? You don't want that the surrounding ambient air affect your result, right? That's why a lot of enos really use charcoal filter, trying to remove moisture and try to remove other gases around in the ambient, right? Okay, all right. Let me show you the Saranos. This is the Saranos that I mentioned earlier, right? A group of 10 researchers, 10 scientists come up with the nano sensor. They have 32 gas sensor. I think they use conductive polymer for the Saranos. They have a sniff, they have in inlet, right, to sniff, and then they also have an inlet as well to push the system, right? Okay, so if you Google around, Inos are good for the medical device, right? They use for the what you call it, to screen, or they use to provide a prediction before the patient diagnosed, right? Okay, I think on our center together with Prof Azhar, I think we are also experiment the same way for medical devices. We are doing for TB and Prof. We are also doing for lung cancer. I think few days ago, I think we are trying to initiate for COVID-19 as well, right? But not for Inos, other chemical device now. Okay, if you take a look, these are the system proposed by Professor Wojnowski from. He was from Irish, but he is in RMIT, I think, in Australia, right? Okay, so these are the device that he designed, right? Uh, these are the sample. The sample need to be heat up, right, at the constant temperature, so that the sample will produce constant smell, right? It will help the solid sample to release smell, and then this smell will be pushed or pumped to the Inos, right? And certain researcher, they also have the temperature block as well, make sure it's in the constant temperature. As you know that chemical sensor, they are severely affected by the temperature or humidity. So you need to make sure that those two parameters are always in constant. And if you have many other variable, you will be difficult to detect the analyte that you want to determine, right? Let's say you sniff one round, the temperature is around 25 degree. You sniff another time, the temperature is 37 degree, right? So of course you will get two different results, right? And then you will think that, or the result shows that the sample are now become worse, right? And in fact, most probably the sample are still the same, but because of temperature difference in your sensor, you get the different result, right? This is what you have to be careful, right? And then of course you need to filter whatever that the air coming through the wire, right? As if you can look detail closely, right? You can see that the what I call it, the tube the push to the Inos, the tube is slightly longer, right? There are ways to make sure that the fresh air goes into the wire and mix around. You you have to make sure that at least headspace air goes to the wire or goes to the sensor, right? So this is able to uh, and how much you need to sniff, right? You need to calculate. Let's say if you sniff quickly, you use 20 milliliter per hour, right? So you are in good range because the smell will not deplete. If you sniff quickly, if you sniff 20 liter per minute, right? Most probably you will get the fresh air coming out from the outside, not from the sample itself, right? So that's why you need to be careful. You need to use the right pump, the right pump rate, so that what you sniff is the headspace, not the air from the outside. Right? So this is also critical as well. Not only the Inos that need to be sensitive or not to be sensitive, but the physics must be right as well. Okay, right. When we talk about the sensor, right, we need to know what are the target, what are the application, our application. Right. There are many other sensor that could be suitable for our application. Right. For example, they have a metal oxide sensor, they have a polymer, they have coating polymer. These are based on the semiconductor sensor. The one that was in Theranos was the coating polymer sensor. right? Lately, there are field effect gas sensor, there are piezo type gas sensor which are using white crystal microbalance (QCM). There are also optical gas sensor, right, whereby you use optical fiber and then you modify the surface of the fiber using a polymer or using a membrane. You also can use a catalytic, right? The one in our car, for example, in our engine, we using catalytic gas sensor because the nature of this gas sensor, it can withstand higher temperature, right? So this is one of the use of the catalytic gas sensor. And I think if you want to go for a specific target, most probably people would choose electrochemical gas sensor, right? With this, you can really define what sort of a target, right? Okay. So again, when you come up with your INOS, you need to know what sort of thing that you want to sniff, what sort of chemical that you want to detect, right? So having that information will help you to choose the right sensor. Okay. And then, although I'm saying this, right, but most of the time we have to experiment few type of sensor because we never know what sort of smell what sort of gases out there, right? Because there are limitation that we can really measure, right? For example, let's say if you want to measure the ganoderma, if you want to measure the smell of rotten fish or meat, first of all, we need to take the sample of gases and then push into the GCMS, right? From there, we can see that a lot of spike, right? And then from that particular spike, we need to isolate which spike or which component that really biomarker or chemical marker for our application, right? There are a lot of uh, tedious process, but normally we can skip or we can do two things at the same time. We try to compare the sensor technology as well, and then also and then by the time we are able to narrow down the analyte that we want to measure. Okay, all right. So these are the catalytic gas sensor. It works by heating up this small dot. When this small dot at a high temperature, it will become very sensitive to a particular gases. Again depend on the material that you use, right? Normally, when we use platinum or rhodium catalyst, these are very good to detect oxygen or any combustible gas in our engine car. Right? Let's say if we want to detect different gases, I think we need to change these two components. Right? We can coated them with gold particle. We can use different chemical, or we can use zinc, for example. Right? So having different material will produce different result. Right? Okay. Since the sensor work in the highest temperature, right? The sensor experience but it will not experience, how I say, will not no need to be clean, no need to be maintained, right? For example, let's say if you use optical sensor, for example, the surface of the optical tip we need to clean out, we need to recalibrate, right? For the catalytic gas sensor, it can stand longer, it can stand for 5 years, 10 years, right? Because it's really suitable in a very harsh environment. Okay, let's move on to the next slide. Chemical ChemFat, normally we pronounce as a ChemFat, right? So the ChemFat is derived from field effect transistor. It is an electronic component, right? Whereby you modify the gate, right? You modify the gap between the gate, right? And then you use different terminal as well to get a different reaction. Yeah. So when you modify the property of the gate or the junction, right? You need to modify as if you can tune to a specific particular gases or chemical. In these cases, for example, you can even use with the conducting polymer to get a specific result. But again, when you use the conducting polymer, you are not able to detect specific gases, but you also able to detect a wide range of gases. Right? Let's say if you really want to go for a specific analyte or targeted, you need to go to the biosensor. Right? This is imagine this is how our bodies work. Right? I think that's the only one that if you can tune to a particular gases, right? Then you have to go to the biosensor, which is not covered in my slide today. Right. And then this, for example, these are another example how chemical gas sensor works, right? So this image was taken from Figaro, right? Few years, I think in 2015, we managed to communicate and to invite Figaro person, right? These are his slide, right? So this is how Figaro work. This plate, we call it metal oxide, need to be heat up at a certain degree of temperature. Normally, it need to be heat up around 300 degree, right? By having at this temperature, the sensing material become sensitive, right? And then it start having or giving a free electron, right? So upon on the analyte, for example, these are the reducing gas. Once this analyte, for example, touch the surface of the plate, it will take out the free electrons, right? And then when you take out the free electron, you'll get a different result, different signal here. So from the signals, then we can differentiate different type of gases, or we can even differentiate the quantity of the gases that was affected the sensing material. Okay, semiconductor gas sensor it's also quite robust because we can heat up as high as possible. When we heat up, for example, the material will goes back to the baseline. For example, let's say if we expose to the high number of concentration, right? Normally the sensor will become how do we say it become numb ataupun tepu. What do you call in English? Tepu, saturated. When the sensor becomes saturated, it need to be pushed for a long time, right? To recondition, right? And to clean the inos, right? Right. Normally, we heat up at a high temperature, and we push through a clean air or zero air. Sorry, zero air. Maybe we say that we push nitrogen, inert gases, right? Then we manage to push out all the reducing gases. Okay, these are the step that are really useful for semiconductor gases. If you take a look on the current trend, now they managed to reduce and make it even smaller. And previously it was big as 50 cent, then it reduced to 5 cents. Now it's even smaller. It's like a tip of your pencil. So, all right, this is how good our technology nowadays. With the help of nanotechnology, the particle, right, the thin oxide on top of the sensor are now can be reduced as well, and it becomes sensitive as well, because you need to apply a little bit of heater, and then the sensor now heat up at the right temperature. Previously, if you heat up the sensor, you can see that the temperature will be different at each different layer, right? So this will also affect the sensitivity as well. But if you have very thin layer, when you heat up, you will have a constant temperature across the layer, right? Then you will get a stable result as well. Okay, right. This is piezo-based gas sensor. You have a quartz crystal, right? The crystal will resonate, right? When it come across with a certain chemical, target chemical, right? Unfortunately, this is not as easy as a metal oxide. When these sensors are saturated, you either throw it away, right, or you need to wash the layer, and you need to what do you call it? you need to put back the element, the substrate on the layer again, right? So it is quite tedious. It is not reusable like metal oxide. That's why in our current Enos, I think we are prefer this technology, metal oxide, compared to the piezoelectric, right? However, the good thing about piezo, we can really narrow down the target gases, right? But again, with that, there comes a drawback, right? For example, if the particular gases have the same molecule, also have the same affinity, you will get the same result, right? And different type of frequency also will affect. You may also uh, get what you call it, get affected by the environment frequency. Let's say when you do the experiment, you have to make sure that you measure in the very good and clean bench, right? You cannot use this and for an outdoor environment, right? If you're going to carry this sensor for an outdoor, you will not get a good result, right? This is where this is another thing, the advantage of the semiconductor gas sensor, right? When you choose a sensor, you need to also to be able to define the working environment. If you want to work in the harsh working environment, the piezo-based sensor, the biosensor are not suitable, right? But if you say that you want to work in the clean environment, I think these are the suitable sensor to begin with, right? Okay, imagine, right? This is if you coated the crystal both side, right? The challenge is you need to make sure that both side having the same amount of sensitivity film, right? When you coat both sides, you have to make sure that you are using, you are dropping the same amount of substrate, right? If you having this one slightly more than this one, you will not get the signal because the signal will be skewed, right? And also the signal resistant, right? And then this sensitive film also is quite tricky as well. You need to put layer by layer. You cannot simply put in one drop, right? So it is quite tough as well. The higher the frequency, the smaller surface area, right? Right. Basically, if you want to measure the concentration, right, we have to use a particular formula. I think it's hard for me to pronounce the Sebron the formula. The change of mass is equivalent to change of frequency, right? So if you have change of mass, when you sensor detect change of mass, your frequency also change. But if you have a different kind of layer on the surface, the frequency will not stabilize, right? So it's quite tricky, but it can be done. We managed to do this as well. Right? We compare with few other sensor, and then it is quite sensitive compared to the metal oxide. Okay, right. So normally this is the result that you're going to see, right? Normally the sensor will resonate at 10 megahertz. If you use 10 megahertz, there are 30 megahertz, there are 100 megahertz, right? The higher the frequency, the smaller the space area, right? The baseline, as you can see that it will be in this flat range, right? When you expose the gas, for example, when you put this ring, right, the analyte will stick to the surface, right? Then your frequency will shift or damper. You will not receive 10 megahertz because of the mass. The frequency will reduce. It will become 9 megahertz, 8 megahertz, and so on. Right. So this piezoelectric, also you can come up with an array concept as well. You can have a different targeted analyte, sorry, different targeted substrate on the sensor to detect different analyte. Right. And you need to make sure that the what I call it, the headspace are homogeneous as well, right? That's why some experiment they put a fan or they put a pump so then they mix around, right? And of course, these QCM-based sensors are very critical on humidity and temperature. Slightly change in humidity and temperature will affect the result. That's why you need a very good environment. The chamber need to be kept constant, the temperature and humidity, right? Unlike the metal oxide, because we have a heater, the humidity will not affect so much, right? But the temperature, of course, will affect. We call it a temperature drift. We will show you shortly in the next few results, right? Okay, let's move on, right? So these are the electrochemical, right? It's quite complicated because you have three different electrodes, and then you have a chemical inside, right? We call it electrolyte, right? This electrolyte will behave as a sensing medium, right? When being exposed to the particular gases or analyte, the chemical reaction will happen here, and then your membrane, your sensing electrode will give a different signal, right? Okay, I'm not so really good with the chemical sensor, right? Let's move on to the optical sensor, right? So the optical sensor is quite straightforward, right? First, you need to have an emitter, which normally people use infrared, and then you need to have a receiver, optical receiver, to detect a change of infrared wavelength, right? So imagine these are the gases, right? Normally, optical gases that use infrared normally it will able to detect CO2, CO, target gases that have a pole or dipole, right? Once you emit the infrared, the what do you call it, uh, the CO, CO2, I think what you call the atom will start to vibrate and it release an energy. So you the energy receiver able to measure the if you will not detect any different energy. But if you shine over the CO2, you have the CO and you have the C and the 2O, right, at the side, then it will resonate and produce energy. So the energy that you measure will tell you a type of gases, right? So that most probably the fundamental behind the optical gas sensor, right? This is one of the approach. There are many other approach. Okay, again, I think these are the summary of this gas sensor that you can see from the table. You can see that carbon nanotube can detect very low sensitivity, right? And works on the conductivity. However, the difficulty it is very necessary and difficult to get repeatability. Let's say if you fabricate one batch, the next batch you fabricate will not get the same batch. Right? So this is always the known disadvantage, right? The optical also very sensitive, right? But again, as you know, it is very expensive and also difficult to miniaturize them, right? It have a longer lifetime, and of course, you need to do maintenance as well. It was not captured in this slide, right? Okay. I think I can share with you this slide so you can have a look later on. Okay. Right. Before we come up, I think before the scientists come up with the INOS, they always use gas chromatography or as we know today, GCMS, right? However, GCMS is very bulky, unable to move around, right? So the scientists need that something portable, something that they can carry over, do measurement at the site, right? There are also some limitation. If you take the sample from the site and then you bring back to the lab, the sample, the target gases might be different from what you see at the site. So this is they call it sample transfer. These scientists come up with a portable enos, meaning that they could do and measure at the site straight away. Right? This is why the enos is quite popular this day. And imagine, for example, you want to detect whether the patient having a cancer or not, right? So it is difficult to bring the patient to the GCMS, right? Although they have done this before, but I think the procedure is not quite popular, right? That's why they have come up with a smaller device. Okay, so let's move on to the headspace sampling. Right? These are normally what people do for the headspace sampling. Right? Take a look on these two different tube, right? Okay. Right. In these cases, what they do is the air or the dry air will having a longer needle, right? Right. When these shorter needles are drawing the air, right? Automatically, because the wire is sealed, right? It will draw naturally from the outside, from the environment, right? And then you either filter this. So these carrier gases will goes in, right, and push to the headspace of the liquid or water. It will mix around. We have to assume that at a certain condition, it will create some certain homogeneous, right? And then when it's mixed around, then this shorter needle will chamber, right? Okay. When it goes to the transfer chamber, right, normally it will retain for a few seconds, then it will start release again. Then after the first sniff, right, the chamber need to be pushed out, then it will push from this side, right? If you take a look, right, this is when the sample gas goes in, right, and then this is when the system push out, right? It will sniff from different